Hi, this is Dick Gross back with Fat Chance, and today we're going to discuss a topic in probability known as expected value. So far, we've calculated probabilities in those situations where there are really only two outcomes. One we call a favorable outcome, the other an unfavorable outcome. And the probability of success is defined as the ratio of the number of favorable outcomes divided by the total number of outcomes. So, for example, the probability of getting a 5 on a roll of 2 dice is 4 over 36. Why? Because there are 36, 6 times 6, possible outcomes, of which 4 outcomes, where the numbers of the 2 dice are 1 and 4, 2 and 3, 3 and 2, and 4 and 1, are favorable outcomes that add up to 5. So the probability is 4 over 36. And this very simple framework allows us to understand a large number of problems. For example, there's a carnival game which we'll call Chuck-a-Luck.
Chuck-a-Luck!
Where you pay $1 to roll 3 dice. If you get a 6 on any of the dice, the house pays you $2. And if no 6 turns up, you lose your money. So this looks like a game of even odds, as each die has a 1/6 chance of turning up a 6. And if you roll 3, you'd think maybe there's a 1/2 chance of turning up a 6. But now that we know how to count, you can see why this isn't true. And the reason is that there are 5 times 5 times 5, or 5 cubed, 125 outcomes, where the numbers on all the dice are between 1 and 5. And there are 6 times 6 times 6, or 6 cubed, 216 outcomes in total. So by the subtraction principle, there are 216 minus 125, 91 outcomes where at least 1 6 appears. And so the probability of a favorable outcome is not a half, but rather 91 divided by 216, which is about 0.42. If you bet $1, then 58% of the time you win nothing, and 42% of the time you win $2. In this lecture, we're going to broaden our outlook to include games where there are several possible outcomes, each coming with a different payoff. In the original game of Chuck-a-Luck, there are just 2 outcomes. Either you win, you get $2, and you lose, or you get 0. But suppose we change the game, calling it New Chuck-a-Luck, by giving you an additional inducement to play. If all 3 dice turn up on a 6, then the house will now pay you $10 instead of just $2 for 1 6. Is it now a good idea to play the game? So now there are 3 possible outcomes for this game, assuming you bet $1. The first outcome is that no 6 appears, in which case you get nothing. The second outcome is that 1 or 2 of the dice come out on a 6, in which case you win $2. And the third outcome is that all 3 dice come out on 6, in which case you win $10. What we need to do to see whether you should play this game or not is to calculate the probability of each outcome and multiply those probabilities by the respective payoffs and add it up. We already know the total number of outcomes, 6 cubed, 216 possible outcomes, of which 5 cubed, 125 have no dice equal to 6. So there are 91 remaining outcomes with at least 1 dice equal to 6, but only one of these 91 outcomes has all 3 dice equal to 6. So the 3 probabilities in this game are 125 over 216, you win nothing, 90 over 216, that you win $2, and 1 over 216 that you win $10. Those are the probabilities. To calculate what the payoff is, we multiply these probabilities by the respective payoffs in the game and add up. And we get the expected return on your $1 bet. So we multiply the probability 125 over 216 by 0. We multiply the probability 90 over 216 of getting 1 or 2 6s by 2, the $2 payoff. And we multiply the probability 1 over 216 by 10, the payoff of getting all 3 6s. When we add up those numbers, we get 190 over 216, which is about 0.879. So the expected return of this game on a $1 bet is about 88 cents. And so it's still a bad bet, even with the promise of getting $10 on 3 sixes. On the other hand, if the house pays out $50 for a roll of 3 sixes, the expected return is larger. It's 0 times 125 over 216, plus 2 times 90 over 216. But now we get 50 times 1 over 216, which works out to 240 over 216, which is about 1.111. And that return is 1.11 on a dollar, which is a good return for you. These are just examples, but you can see how much more flexible this method is. We can now play games with many different outcomes, each outcome having a different payoff on a bet of 1 unit. We calculate the expected return on such a bet, which is called in probability the expected value of the game, as the sum of the respective probabilities times the respective payoffs. Let's do one more example, a more complicated game. Suppose we roll 5 dice, and you bet 1 unit. If you roll 3 of a kind, you win 2 units. If you roll 4 of a kind, you win 10 units. If you roll 5 of a kind on the 5 dice, you win 100 units. And if you don't have 3 matching dice, you win nothing. Notice that we haven't specified whether you're betting $1 or €1 or 1 yen. The payoffs are just in the same unit of currency as the bet. So we can just notate the payoffs by numbers. And to calculate the expected value, we need to work out the probabilities of each result, multiply by the payoff, and add up. To begin with, the total number of outcomes is 6 to the 5th power. We're rolling 5 dice. Each roll, there are 6 possible outcomes. By the multiplication principle, the total number of outcomes is 6 to the 5th, or 7,776. Of these, exactly 6 rolls give 5 of a kind, because we have to specify 5 of what? You could have 5 ones, or 5 twos, or 5 threes, 5 fours, 5 fives, or 5 sixes. So that's 6 rolls, and the probability of getting 5 of a kind is 6 over 7,776. Now, to count the number of occurrences of 4 of a kind, we first specify which number comes up 4 times. And again, there are 6 choices for that, and there are 5 choices for the number on the other die that comes up. But that number can occur in any of the 5 places of the sequence of the dice. So by the multiplication principle, the number of rolls that come up exactly 4 of a kind is 6 times 5 times 5, 150, and the probability is the ratio 150 over 7,776. Finally, we have to count the number of rolls that come up exactly 3 of a kind. There are 6 choices for the number that comes up 3 times, and there are 10 choices for the places where it comes up, because 10 is 5 choose 3, the 3 places out of the 5 rolls where that number appears. And once we've specified that, there are 5 times 5 choices for the numbers on the dice in the remaining 2 places. By the multiplication principle, the number of rolls with exactly 3 of a kind is 6 times 10 times 5 times 5, which works out to be 1,500, and the probability of such a roll is 1,500 over 7,776. And now that we have these 3 probabilities, we multiply them by the respective payoffs and add them up to calculate the expected value of the game. And this works out to be 6 over 7,776 times 100, the payoff for 5 of a kind, plus 150 over 7,776 times 10, the payoff for exactly 4 of a kind, plus 1,500 over 7,776 times 2, the payoff for exactly 3 of a kind, and that works out to... Now, wait a minute. We haven't considered the 4th outcome. We haven't yet calculated the probability that no 3 dice match on a roll of 5. But to calculate the expected value of this game, We don't even need to do this. And the reason is that in the formula for the expected value, we multiply this probability by the payoff. And the payoff for getting no 3 dice matching is 0. So it doesn't even change the expected value, whatever the probability is. But if we wanted to calculate the probability, we could. And remember that in the probability version of the subtraction principle, the sum of the probabilities of the 4 outcomes has to add up to 1. Something has to occur. And since we've worked out the probabilities of the other 3 outcomes, we can find that the probability of no 3 dice matching is 1 minus 6 over 7,776 minus 150 over 7,176 minus 1,500 over 7,776, which works out to 6,120 over 7,776. Let's end with a general formula for expected value that covers all the cases. Suppose we play a game that has n possible results. If the probability of each result occurring is given by P1 for the first result, P2 for the second, all the way up to Pn for the nth result, and the payoffs for each result are given by A1 units for the first result and A2 units for the second result and An for the nth result, then the expected value of the game is defined by the formula EV, expected value, is P1 times A1, the probability of the first times the payoff for the first, plus P2 times A2, the probability for the second times the payoff, all the way up to Pn times An. That's the formula for expected value. We also know in this expression that the sum of the probabilities is 1, because some event must occur. 1 is the sum P1 plus P2 up to Pn. Okay. Now remember, another thing is that if any of the payoffs are 0 for that outcome, you don't need to calculate the probability of that outcome to determine the expected value, because you're going to multiply that probability by 0 in the expected value, and it won't contribute to the sum.